Okay, so why is the Lagrangian density more interesting to us than the Lagrangian itself? So I want to remind you, what's the benefit of the Lagrangian formulation of mechanics? Well, we said the benefit of that was that we could build in symmetries into our equations of motion most simply. So what do we want here? Well, we're really doing field theory so that we can build equations of motion that are Lorentz invariant. That's what we're after. We want to build equations of motion that are Lorentz invariant. Now, what does that mean? Well, let's imagine that I'm in my frame and I've found some solution. So let's say my solution is called f of x mu. So f of x mu is a solution. Now, you are in some boosted frame with respect to mine. And to get to your frame, I have to perform a Lorentz boost lambda. So f of x mu is the solution that I write down. You would write it down as f of mu x mu, because that's how our frames are related by this boost. Now, I want us to agree on what the laws of physics are. So I want you to be solving the same equation as the equation that I'm solving. So if f of x mu is a solution to my equation, I also want this boosted function to be a solution to the same equation, because this is the solution that you would write, and I want you and me to be solving the same equations. So this is what we mean when we say we want the equation of motion to have a symmetry. When we say we want equations of motion that are Lorentz invariant, we want Lorentz transformations must map solutions to solutions. Okay, so if I've got one solution to the equations of motion and I perform a Lorentz transformation, I want to get another solution to the equations of motion. Now, how did we say that we achieve this? We said build an action S that is Lorentz invariant. Now, what does that mean if the action S is Lorentz invariant? That means if I work out what is the value of the action evaluated on the solution, f of x, I get exactly the same value for the action if I evaluate it on the boosted solution. So this is what we mean when we say that the action is Lorentz invariant, okay? So when we say build an action that is Lorentz invariant, so build an action that is Lorentz invariant, this is what we mean. The value of the action will be the same if we evaluate it on two boosted solutions, two Lorentz transformed solutions. But the point is, solutions to the equations of motion minimize S. So if you want to know, do you have a solution or not, evaluate the action of that solution. And if it's a minimum, then it is a solution. Well, if S of F is a minimum, then so will S of F evaluated on lambda X. That'll also be a minimum. So we have guaranteed by getting our equations of motion from the condition that delta S is equal to 0, we have guaranteed that if the action is Lorentz invariant, then Lorentz transformations will map solutions into solutions. Great. Okay, so now let's take a look at the action. So what does the action look like? Well, the action S is given by an integral dt of the Lagrangian. Now, if we look at this, we know that the action S has to be Lorentz invariant for the reasons that we've just explained, okay? This is how we're going to get Lorentz invariant equations of motion. But if we look at dt itself, well, dt is not Lorentz invariant. And the reason why it's not Lorentz invariant is because of time dilation. So dt is not Lorentz invariant. S has to be Lorentz invariant. It's equal to dt times L, and dt is not Lorentz invariant. That means L is not Lorentz invariant. It has to transform in a complicated way so that L times dt is Lorentz invariant. So the Lagrangian itself is not Lorentz invariant. If you wanted to construct something that transformed in the correct way, well, that's a complicated problem. Constructing a Lorentz invariant is easy. We'd take 4 vectors, we would contract their indices, that would give a Lorentz invariant. We've got lots of ways of building things that are Lorentz invariant. But you can't use any of that knowledge when you're constructing the Lagrangian. The Lagrangian transforms in some complicated way, and you would really struggle to work out what the Lagrangian is just using that transformation property. So working with the Lagrangian is hard. It's not a good idea at all. But let's plug in this formula that we've got for the Lagrangian. Well, we would have an integral dt, an integral d3x, and then the Lagrangian density. And this, of course, I can just write as the integral d4x times the Lagrangian density. Now, if we perform a Lorentz transformation, well, dt is not Lorentz invariant because of time dilation. So times get stretched out. But d3x is also not Lorentz invariant because of length contraction. Lengths get shortened. So we're making dt bigger and d3x smaller. Well, the product of the two is Lorentz invariant. How would you check that? Well, you'd calculate the Jacobian for the change of coordinates that corresponds to a Lorentz transformation, and you've already done that exercise, and you found that the Jacobian was 1. So d4x really is Lorentz invariant. And what that means is the action which is Lorentz invariant is equal to d4x times the Lagrangian density. d4x is Lorentz invariant, and that means the Lagrangian density itself is Lorentz invariant. So to construct the Lagrangian density, you are going to want to construct a Lorentz invariant quantity, and that is a straightforward exercise. So that's the reason why we prefer to focus on the Lagrangian density and not the Lagrangian. Good. Okay, let's clear a little bit of space. So the next thing that I want to think about is the conjugate momentum. So this is something that we know how to calculate. So what does the conjugate momentum look like? Well, when we are dealing, so this is our column for one particle. Well, when we're dealing with a single particle, the conjugate momentum, P of t, is just equal to the derivative of the Lagrangian with respect to q dot of t. And if you look at the Lagrangian just sitting above, the first term has got q dot in it. Differentiating q dot squared, we just get 2q dot. So plugging it in there from the first term in the Lagrangian, we just get m q dot of t. And from the second term, the potential, that doesn't depend on q dot. So that doesn't contribute at all. So we learned that P of t, the momentum, is just m times by q dot of t. There's a very natural generalization of this to n particle mechanics. So let's write it over here. Each particle would have a momentum. So let's call it PA of t. And this would just be given by the derivative of the Lagrangian with respect to q dot, but now a of t is an index a. And what is this equal to? Well, when we come to differentiate the Lagrangian, we have to differentiate all of the LA's. And there's only one LA which depends on QA dot, and that's L with A. And if we differentiate the QA dots, we get a 2QA dot. So we'll end up getting MA QA dot as a function of T. And when we differentiate the potential, that doesn't give a contribution. So this looks nice and sensible. The momentum of the 8th particle is just the mass of the 8th particle times the velocity of the 8th particle. Okay, Now let's come to calculate the conjugate momentum for field theory. Well, let's denote the conjugate momentum by pi. You'll see that the momentum in the n particle case was labeled by A, so pi will include x as a label. So it'll be a function of x and t, and then it will be given by a derivative of the Lagrangian density with respect to d. Now, we've got here q dot, so we'll have a phi dot. We need the dependence on A, so this is an x and t. And this will be the conjugate momentum for the field. Okay. Let me, in fact, do just one thing. Let me say that this was a derivative of the Lagrangian for the eighth particle, LA, because it's LA that is the natural analog of the Lagrangian density. So in this way, just take a look at these three boxed formulas. Oh, didn't want that. Here we go. Take a look at these three boxed formulas. They lead naturally from the momentum for a single particle to the momentum for n particles to the momentum for a field. So this is the natural generalization. Great. We'll continue in a moment.